Binary tree is a tree data structure in which each parent node can have at most two children. So there are number of nodes in a tree. So there are some internal nodes, one of these is a root node. So all internal or parent node can have maximally two children. So either they can have one children or one child, or two child, or no child. Okay, so the maximum possibility is either zero child, or one child, or two children, not more than that. If a node is having more than two children, so it is not a binary tree. Okay. So there are various variations of binary trees, such as full binary tree, complete binary tree, degenerate tree, perfect binary tree. Types of binary tree. Full binary tree. A full binary tree is a special type of binary tree in which every parent node or internal node has two or no children. Okay, so here each parent node or internal node can have two, or no means zero children. Okay, so what are the parent or internal nodes? Here one is a parent node. Yes, it is one is a parent node. Then two is a parent node. Then 5 is a parent node, and rest of the node 4, 6, 7, 3 are the leaf nodes. So we are only talking about parent node or internal nodes. So these are the parent or internal nodes. They can have either 2 or 0 child nodes. So one is having exactly 2 child nodes. Okay, perfect. The node 2 is having exactly 2 child nodes. Perfect. The node 5 is exactly having 2 child nodes. Perfect. Hence all the internal nodes follow this criteria of having either 2 or 0 child nodes. So hence it is a full binary tree. Perfect binary tree is a type of binary tree in which every internal node has exactly 2 child nodes, and all leaf nodes are at same level. Or internal nodes means 2, 3, 1, all these nodes are having exactly 2 child nodes. So 1 is having 2 child nodes, then 2 is having 2 child nodes, and 3 is also having 2 child nodes. Okay, the first condition is okay, and all the leaf nodes are at same level. So these are all the leaf nodes, and these all are at level 2. Okay, so this is level 0, this is level 1, this is level 2. So all leaf nodes are at level 2 and in a same level. So hence it is a perfect binary tree. Complete binary tree. Complete binary tree is just like a full binary tree, but two major differences that are every level must be completely filled. So at every level there must be a nodes. Okay, and there should not be a empty spaces in a level. Okay, so this is a level 0, this is level 1, this is level 2. So you can see here all the levels are filled except this last node is not having the right child. Well, we'll see what is this. All leaf elements must be from lean towards the left. So these are the leaf nodes, and all are tending to the left side. So this is the left side and this is the right side. So all leaf nodes are towards the left side. Okay, so this condition is fulfilled, this condition is fulfilled. The last leaf element might not have a right sibling. So, okay, so the last leaf may not have the right sibling. So this node in red color is absent here. So this is a sibling which is not present there. So it is not there. So it is filled from the left side but empty at the right side. Okay, only in the leaf node. So it is satisfying all the condition. Okay, so it is a complete binary tree. Degenerate or pathological tree. A tree having a single child either in a left side or a right side. Okay, each node will have a single child either in the left side or a node having in a right side. So this node is having a left child, this node is having only one right child, this node is having only one right child. So a node will have either a left child or a right child, and such a combination or in a left or right directions will create a tree like this, and this is nothing but the pathological tree. A variation in pathological tree which is called as a skewed binary tree. This is the variation of special case of the pathological tree where it is either dominated by the left nodes or a right node. So all the nodes will have only one child, and all will be the left child, or all will be a right child. If all are the left child, then it is called as a left skewed binary tree. If all nodes are at the right side, then it is called as a right skewed binary tree. Array implementation of a tree. So this diagram I want to show you how we can represent a tree in an array. So this is the tree, which 5 is a root, 3 and 7 are the children of 5. Then 3 is having one child, which is 1, and 7 is also having one child, which is 9. But for 3 the right child is missing, so right child is not there. For 7 the left child is missing, it is null. Okay, so we'll just represent this tree in an array like this. So we'll write here the numbers. So we'll write at the root 0, then this is 1, this is 2. So from top to bottom and from left to right. Okay, we'll make a numbering 0, then 1, 2, then this is 3. So this node is null, so we'll still it is null, we'll number it. So it is now 4. So if this is also null, so we'll number it as 5. So this is last node, which is a 6. So there are total 6 possibilities of nodes here. So these numberings are nothing but the position in a array, like this 0 to 6. Okay, so this is the array. So at 0 we'll store node 5, at 1 we'll store node 3, at 2 we'll store node 7, at 3 we'll store node 1, then at 4 there is a null, so we'll have an empty space. At 5 there is a null, we have an empty space. At 6 we are having a 9. So this is nothing but the array representation of this tree. So how this relationship works, so we'll see with the help of this diagram. So this is another tree, 0 is a root, then 1 and 2 are the child nodes of 1, 0, then 3, 4 are child nodes of 1, 5 and 6 are child nodes of 2. So this is the array A. So how to represent this array, how this array representation works for this tree. A of I means if this is a 0th location, this is a 1, this is the 2, and likewise. So A of I has a children's, so each node A of I is what, nothing but the location in array, will have two children, a left children and the right children. So if A of I is a node, then its children, left children is at A of 2i plus 1, and the right children is at A of 2i plus 2. So if I is 0, then the first children is nothing but A of 1. So this will be the first children of this, and if you put 0 here, A of 2 will be the right children. So for A of 0, A of 1 is a left children and A of 2 is a right children. This is another implementation of a tree, which is called as a linked implementation, similar to the concept of linked list. Linked representation. A tree data structure can be created by creating nodes dynamically with the help of pointers, similar to the linked list. A tree is a tree. The tree in the memory can be represented as shown below. So we'll create a node, a structure node, and the node will be like this. It will have three parts. First is a left pointer, then the data part to store some data like a character or an integer, then the right part. Okay. So this is a node we can create with the help of structure like this: struct node int data, struct left pointer, struct right pointer. And this node we can allocate a memory dynamically at a runtime using malloc and calloc function, and whenever we don't want a node, we'll free the node. And a structure can be created like this. If this is the root node, so it will have a left child, a right child. So this arrow is just a pointer to the another node. Okay. And if the node doesn't have any child, so we'll write here null in a pointer field. So if left part and right part both are null, means this will be a leaf node, and this will be a implementation using the linked representation.